It's going to be death by Semgrep these next few weeks for you guys and gals. I love that. So absolutely, thrilled to be here. Thank you so much. We love participating in OWASP chapters, and this is my first time with the LA group. I don't know if I'm going to match Brandon's charisma, but I'll give it to him here. I'll only take a few minutes, but really just want to introduce the team to Semgrep if you're familiar with us or if you aren't. We've been up to a lot, right? A lot of people know us from our open source roots that I'll talk about, but there's a lot of other cool things we have going on here. So like I said, as some of you may know, Semgrep has open source roots dating back to sgrep, which we essentially reignited and ultimately became Semgrep. We continue to be the maintainers of that. We now call it our community edition. But really our focus lies on supporting our customers like Figma, Dropbox, Slack, you name it, with our multimodal AppSec solution. Our goal is to make it cheap, to make it expensive, to exploit software. A little bit of a mouthful, but that's what we're looking to do here. What's multimodal, you ask? I think Eric had it on his slide or for the talk next week. I'll touch on that here in just a few slides. But overall, some metrics just to drop here. So there's over 50 million open source downloads, over 10 million scans running a month. Semgrep's most widely deployed code scanner in the world. There's over 3,500 community roles and over 30 languages supported. A lot of disruption going on in the space. That's probably an understatement. There's a lot of unknowns, but there's a few things that we do know, right? So software is the backbone of pretty much all businesses in every industry. And software development is continuing to accelerate, right? And that's only getting even more, continuing to increase with AI coding tools. So with the velocity gains, which are absolutely worth it, it's also expanding the attack surface, introducing new blind spots, and generating even more noise, which seems to be the issue that we can never get away from in AppSec, but we're trying to. Few other things here from studies, right? So it shows or has been found that AI-related vulnerabilities from AI-generated code are 5 times more likely to be criticals and highs. A lot of teams on average are seeing over 100 new daily vulnerabilities at this point. So again, backlog just continuing to increase. And it's 252 days right now on average to fix a vulnerability. So all of these numbers are increasing and going in the direction of up, which is, quite frank, the opposite direction, right, of what we want to see them going. Given those challenges, of course, and what we're hearing, we've been endlessly building to ensure Semgrep is best prepared to support our customers as well as the community as the space continues to evolve. So our goal remains, right, to move fast without adding a bunch of security friction. So you can see here our 3 products at the top, right? First-party code, whether it's written by a human or a bot, third-party code, and exposed credentials. And we want our solution to get smarter as you build, right? The more you use Semgrep, the more it should know your organization and curate kind of the determinations that it's making. Again, I'll share a bit more on that. And keep developers, of course, in their flow, the tools that they use, just so you're shipping quickly with confidence and securely. One of the new things we've been working on, we actually just introduced this at RSA, is what we're calling our Semgrep multimodal approach. So historically, we've had our rule-based engine that's still very much a key piece of our solution, a key foundation, and there's a lot of value there with cost and efficiency. But what we've done is marry those rules with inference capabilities to deliver the best of both worlds. The 2 of them independently are good, pretty good, but the 2 of them together are actually proving to be the best outcomes that customers can get. Some of us internally like to call this the peanut butter and chocolate story, right? The better together, the Reese's cup of AppSec. And our team's battle tested this, right? So they've taken our multimodal approach against foundation models purely, and you can see the results here, right? Finding more more true positives and significantly reducing the false positives. Just to double click a little bit into those stats, and I definitely linked the blog post here, way too small. I'll drop it in the chat after. But this just dives in a little bit more to like what our research team has found, right? As they've tested Semgrep against, Claude, OpenAI, and how Semgrep has come out over top in terms of accuracy and the findings that we're seeing. AI is definitely woven throughout the rest of our platform in other ways, right? Aside from what we just spoke on. So you can see here detect. So we have AI detection. Traditional, SAST scanners are not great at finding like OWASP business logic vulnerabilities, IDORs. Those are things that AI detection with context are a lot more effective at. You can see here for filtering, think of auto triage. So every finding that Semgrep services, we like to have a broad net at first, and then auto triage will actually, help you prioritize and filter through the likely true positives for your team with pretty extreme accuracy that I'll touch on. Generating auto fixes, right? So leveraging that to produce and test the fixes for your team and make sure that your devs or AppSec team can push those confidently. And then preventing these, right? And also continuing to tune determinations by something we call memories. What do these actually look like in practice, you ask, Megan? I'll touch on that a bit here, focusing on kind of this screenshot that showcases a finding that had auto triage done by Semgrep. So you can see there in plain language, it says like, hey, likely false positive. The accuracy, we've had this capability. This is like a built-in Semgrep workflow. We've had this capability for well over a year now. But the accuracy that we've seen from our security research team is upwards of like 96%. And from our customer feedback is 95%. So we're never going to say like false positives will never happen because we just don't think that's a reality for unique organizations. But we're getting nearer to that goal of reducing that burden for your team. Additionally, here's an example of memories. You can think of these as like plain language rules or prompts that auto triage can utilize as it makes its determination. So as it's looking at the findings, this is a really easy way to add, again, organizational context. This is something AppSec teams can do within the platform. It's something developers can help craft as they're responding to suggestions or findings directly in a PR, maybe in like GitHub or GitLab. And so with these, you can see the impact on some of these here. A single memory, the whole objective is that you craft a memory, you triage a false positive once, and you never have to triage that same one again. You can scope these memories by like projects, repos, and it's not like you need a ton of them to see pretty significant results. So teams have had a lot of success and impact from this. The last or kind of second main concept aside from multimodal that we've recently launched at Semgrep, super excited about. So again, we've had some of these like pre-built Semgrep workflows that have been running and been awesome for us, right? So AI detection, auto triage, you see here, auto fix. But there's some new capabilities in purple that we want to give teams the ability to customize to create their own workflows aside from some of the ones that we already have running within Semgrep. This is super early stages for us, but we're super excited about it. I want to say we have it in a private beta right now. But just to give like a high level example of that, right? So here's a workflow. It's pretty common across, AppSec teams and engineers. Your tool finds a vulnerability. You research the issue, determine if it's worth fixing. If it is, you open a ticket, figure out who owns the code, and then maybe you propose a fix, right? And then hopefully that issue is resolved. So while the overall flow may look similar across customers, the individual components look different because they need to adapt to your unique business, right? So we're giving teams the ability to build that within Semgrep, which has been great because teams are already building these workflows honestly on their own, but there's concerns around the maintenance of those, right? The token costs of those workflows. How do you really validate that they're continuing to run? Building these within Semgrep give you those confidence and efficiency across, kind of those concerns for our customers. That's all I have on the slide pieces here. So really appreciate the few minutes just to talk about what we're building, what we're excited about. I'll drop these links as well here. But a lot of great ways to interact with Semgrep, right? So you can play with some of the rules. You can try Semgrep Community, which is SAST only. You can also try Semgrep Multimodal for free for up to 10 developers. So for any like personal projects or if you're at like a smaller organization, like please get in there, test it out. We do have a community Slack channel, so I'd love to engage with you there. And then didn't really touch on it much today, but we do have an MCP server as well that's available for you to use. I'll drop those. And then, really, last but not least, we're going to be raffling off a $100 Amazon gift card at the end of tonight's meeting. So if you want to participate or be in for the drawing, go ahead and scan this QR code, and we'll announce the winner here after Brandon.
That's
And
my
we
name.
can give it to the people that they are sorry that they ask questions. So we encourage people to engage into like your Q&A.
Yes, absolutely. And I was going to say too, I had it teed up for us, but I have a few of those links here that I had shared throughout. And I'll leave this up just for a few more moments here. And if anybody else needs it, I'm sure Amanda and I can find a alternative way to get you in here. But with that, any questions? Brandon and I certainly can help answer. Again, you're going to be seeing Eric next week as well. But I just saw Doug hop off. Doug, did you have a question?
Yes. Um, I'm driving, so could you please put the QR code in the chat or the link?
Yes,
There's nothing I
absolutely.
can do with it.
Yeah,
Thank
and
you.
it looks like Amanda actually just did that already for you, Doug. So definitely don't do this while
I
driving. We
got your
advise
back.
against that. Be safe. Don't do this while driving. Yes, and tag in any of us, and we can get you submitted on our side.
Thank you, Amanda.
Perfect. Thank you, Megan. So any more questions?
Oh, yeah.
Got it.
Do you have specific examples? I've spent most of my life writing new code that nobody's ever seen before. And I recall a security breach we had in the Linux kernel years ago. Someone fixed a warning, and suddenly SSL you only had to go through 256 permutations to break any key. Oh, yeah, because a warning was fixed. The person who coded that, I have no idea who it was, uh, knew that that warning had to be ignored, but some automated tool said, warning, fix it. And it fixed it and created a massive security breach. How do you handle stuff like that?
It's a good question. I'll probably actually default to Brandon
Yeah, so you're
if you
saying
have a
that this
perspective
automated
there.
Yeah, so you're saying this automated tool caused a quote unquote fix that caused a error that made there be a vulnerability in the kernel? Is that what you're saying?
Well, it was either kernel or SSL.
Sure. Okay. I'd say that the biggest thing about that, and I think this is actually very applicable to the subject of the talk we're going to be saying. So thank you. For the other people in the room, Bill is not a plant. What's interesting about that, I think, is I think you always need to have a human in the loop. I think you need to have as much as possible like someone that is aware of what's going on and not just like applying things in an automated fashion and not knowing what's going on. So like, yes, Semgrep has these things called auto fixes that can automatically remediate code and apply fixes that we think are going to make a vulnerability go away. But at the end of the day, it's up to the engineer, the human, to approve that and merge it in. You know, if you're blindly merging in things like tools tell you, sure, the fixes are only as good as the tools, I'd say. But I would always fear, for like, wrecking some code or smashing something that we shouldn't have when there's not kind of the permissive layer of authority, if that makes sense.
Interesting. The way I found out about that problem is one of my clients were compromised, and I was on a flight talking to a security person, I'll put it that way. And I said, I don't understand how they could break through SSL in minutes. And then he said, oh, did you know about the warning? So people in the know knew about the warning, the issue with the kernel and with SSL, but not very many people, like developers, knew. Now, this is kind of a problem because in the kernel and stuff like this, there are all kinds of implications that if you fix this one thing, it'll cost something else. How do you address that?
So you're talking about if you were to fix something, it'll cost you resources, it'll cost you time, it'll cost you energy. That's what you're saying?
Well, recently there was a comment, someone said they found 1 million security issues in the Linux kernel or something like that, some craziness. And I was thinking about all the things in the Linux kernel where something was written by someone knowledgeable about it. And if they changed that code, they would have to test it.
Mm-hmm.
If they assumed it was bad, they would have to be able to understand why it's bad. So I understand that we need to always check return codes.
Mm-hmm.
That's pretty obvious. But sometimes you check a return code and you can't just return. You have to do something specific because you're in a specific place in the movement of data through the kernel. These are subtle things.
Yeah.
So how do you address them?
Yeah, that's a really good question. I think that this kind of goes into the themes of what we'll be talking about today. So I think it's like a very good question that we're kind of aiming to try to answer, and in all areas of AppSec. I think, would you mind if we continue this after the talk? Because I think I have to kind of get going here, but I'd love to stay afterwards and talk with this about you and anyone else who wants to listen. If that's cool. Cool.
Okay. So, Brandon, you
Yeah.
can start your talk if you want, and then later, let's just like continue with any question that anybody has. Please.
Yeah,
Thank
sure.
you.
Okay. And I do mean that. I will stay afterwards and talk for how long as people would like to. So for real.
Perfect.
Cross my heart and hope to die.
Thank
So
you.
it's funny how people say you get to start your talk because for my perception, I've been talking here already for like some time. So like you can start your talk, like I have been talking. It's like funny how that works. Let's go ahead and start the presentation, shall we? So everyone can see this fine. Yeah, I think that was good. Okay, so today we're talking about this talk I made for B-Sides SF technically, but we're repurposing it today, which is called 1001 AI Prevented CVEs. This was for a talk that was so B-Sides had a theme which was musical theater, which I'm very enthusiastic about. So I themed my slides after it. So there might be some obscure musical theater references that are not actually relevant at all in today's particular setting. So do with that what you will. But the subtitle is Vibe Coding a Whole New Supply Chain Defense. The reason for that is because I thought that this talk had a higher chance of being accepted if I put vibe coding in the subtitle. That's only partly a joke. But actually it is a little pertinent to what we'll be talking about today, which, as with every other talk happening in the computing sector in the past, 2 years, this talk has to do with AI. It is worth noting that I am not what I'd call an AI guy. I'm actually very much a principalist. I'm a programming language theory enthusiast. I'm a functional programmer by trade and by training. And so I very much believe in more principled, formal guardrails and approaches. So this talk is actually a synthesis of both of those things. It's me talking about how I view things as someone who believes in a little bit more discipline. Okay, software supply chain. That's like a thing that we've all heard about. That's a thing that's been pretty important, I'd say, in the past little while. We can give you some numbers. Here, people love numbers. Here, have some numbers. 50,000 estimated supply chain vulnerabilities in 2025. Wow, big number. Up from 40,000 in 2024. That's 20% for those of you keeping track at home. We've all heard about Shai Hulud, React to Shell, Langflow. It seems like every other day there's some kind of supply chain attack that's very, very, very unfortunate and bad and high profile. I think that the CEO of Semgrep literally has a domain called days since last supply chain attack or something.com, not or something.com. .com and or something, it gets reset every pretty soon, right? Pretty often. I think that literally didn't happen like 2 weeks ago or something like that. It's like all of this stuff is happening every single day. And it's like, how do we deal with these supply chain attacks that are really quite bad? So we're Semgrep. We build an application security platform that Megan was so kind as to share the details about with you. But the question is, for people who are building application security tools and also for the consumers of those such tools, practical question is, what does it take to build a quote unquote mature supply chain product? What does that entail? How do we make a supply chain product or a supply chain tool mature? Right. And this is kind of like an agnostic question to the particular vendor, I would like to say. So my claim to you, I'm a big detection guy. I like detections. I like writing program analysis tools that find things. What I'm going to tell you today is actually that's not enough. How good your tool is at finding things. First of all, you're always up against the clock against Rice's theorem, right? Undecidability. You cannot write a program that detects all such properties or any such property about all programs, right? Flip the quantifiers however you like. You can't do it. It's just no, right out. Like God said we can't do it. Sorry. So detection is not enough. But what else can we do? We need to be able to keep up with the oncoming flood of vulnerabilities because there's a lot of them. 50,000, I think I said on the last slide. Let me introduce you to my friend Max. Max isn't here today. This is a real person, Max. I sit nearby him, but he's a security researcher at Semgrep. Here's what he does. All right, and this talk is kind of me getting at some like abstract, more general principles by telling you about specific use cases within that we've encountered, that I think other people have encountered. So I will tell you a degree of parables today, but I would like you to take away something a bit more general from this, I should say. Also, I don't believe in the fake speaker speak-e relationship. And so anytime if you have questions, please just like interrupt me. It's fine. I don't care. Okay. Max wakes up. Here's what he does. He checks the queue. Security researchers at Semgrep, when there's a CVE, a supply chain vulnerability filed in a library of some kind of package, it is filed overnight, and then Max gets it in his queue because there's a new vulnerability. We have to remediate that. Cool. How we want to do that is we would like to write what's called a Semgrep rule. I don't know if any of you have used the Semgrep CLI tool, but basically Semgrep is a program analysis tool that finds things, right? And it finds things based on the rules that you write. So it's a query language that you can specify some kind of query, and then it'll go and find it in code, okay? The ideal is that we should have for every single one of those CVEs a query, a rule that detects the uses of that vulnerable package at the vulnerable versions. He then needs to like read the vulnerability description, like what the package does, how people use it, and the commit that fixed the issue to try to figure out like what it is about the code that was fixed. And then click through the source code to figure out what else about the code is like vulnerable or could be vulnerable. So what I'm trying to get across to you is this is a very intensive process. It's annoying. It takes a lot of research. That's his role. And for each CVE, we have to write what's called a Semgrep supply chain rule, a rule that tries to detect vulnerable uses of this package. A lot of work. Now, I don't know about you, but that sounds like a lot of work to me. So the problem is that Max may never have seen this package before. Let's suppose that you're like a security researcher and you see this like package LangChain or TensorFlow. All right, let's suppose you haven't used either. You don't know what this package does. You don't know what the code looks like, but there's a vulnerability and you have to read all this code. You have to click through. And I don't know about you guys, but I think that one of the worst parts of having to onboard to like a new code base. Well, let's just say it sucks to onboard to a new code base. That's all I was going to say. You don't know what's going on. You have to click through all this code. It's a little bit better now that we have Claude and stuff, but it's a lot of work, right? So Max has to go read through all his code. Let's suppose that he like searches GitHub to find how people use the library, and let's suppose like this CVE, it is fixed because there was a single private utility function in the library that was vulnerable. That function might be used in like 20 or 30 places in the package. And now we have 20 or 30 places in the library, like TensorFlow or LangChain, that might be vulnerable. We don't know. It is transitive, right? It flows through the uses of these functions. So after 30 minutes of clicking through source, he makes his best guess. Maybe this one's vulnerable, maybe this one's not, and then boom, 20 more vulnerabilities to go. Oh man. Guess we're not sleeping tonight. A lot of work. So, like any good engineers, when we identify a grueling, tedious workflow, we'd like to simplify or make obsolete that workflow because we don't want to have to do all that work. So this is the problem that we're going to talk about today, is how do we make the process of remediating supply chain vulnerabilities automatically, ideally, easier? So obviously this workflow becomes untenable as you get more and more CVEs. If 200 CVEs are filed tonight, which by the way can happen and has happened, your security researchers or like your ability to remediate against them is going to be much more difficult. Also, there's a lot of programming languages out there in the world. Okay, I saw this like Hacker News thread earlier where someone was like was challenged at a party to name 40 different programming languages. It's like there's a lot of programming languages out there, and those programming languages have frameworks like I don't know Next.js or Django or what have you. So each of those languages and frameworks multiplies to make more and more of an attack surface that you have to be able to defend against. And each rule costs us expensive human resources, as you all are aware, as humans, not as resources. You guys are just humans. I don't mean to call you that. We need an approach that will scale with the volume of supply chain vulnerabilities, and we need one that will cost less in researcher time. So let's automate this. Well, hello, my name is Brandon. I'm a program analysis engineer at Semgrep. I think a lot about programs, and I think a lot about programs that think about programs. And I would go farther, but that's actually pretty much where it ends. I've been working at Semgrep for about 4 years since I graduated from Carnegie Mellon, where I was educated in computer science, and I previously have lectured there on the subject of functional programming. So I like functional programming a lot, but I also like program analysis and security a lot. We are a security company, and I don't need to tell you more about that because Megan gave us a lovely synopsis of that already. So I don't need to go more into that. But our mission to profoundly improve software security. So let's do that, shall we? Okay, let's talk about how vulnerability happens, right? Starts and ends in the code. I'll introduce a little bit of vocab, which is that we have the introducing commit, right? When a vulnerability happens, either the vulnerability was there when the code was originally written, or somebody later like merged a PR, introduced it via some commit that made that vulnerability exist. There's also a disclosure. That's when the general public becomes aware of the vulnerability. That's the CVE term I was using for. I say a CVE, that's the vulnerability, that's the disclosure. So the CVE system will give it its number. We also have what's known as a patch commit. That is the change that's counter to the introducing commit. It's the one that fixes the vulnerability. Usually when the CVE is published, it will have that patch commit with it because they only, they'll disclose it with the fix because obviously they won't, I mean, not always, but like usually it'll be disclosed with the fix because they want to fix it. And I would also say the vulnerable range is all the ranges of versions between the introducing commit and the patch commit. So the range of, things you could have installed the package at to still be vulnerable to that vulnerability. Say that 5 times fast. Okay. SCA, software composition analysis. What's our job? Well, when a package with the CVE is used by a consumer, so let's say you are like using your like Java project or whatever, and you import Apache dot whatever, or you're using Python, and you import, I don't know, NumPy or Matplotlib or whatever. Those are your packages, right? And you are the consumer. Our job as Semgrep supply chain is to scan your first-party code for uses of third-party code. Third party being like a library, like a package, like stuff on GitHub, open source stuff. And also because we can scan the open source stuff, because it's open source, we can then use that to inform how we know whether or not your first party code is vulnerable. So we want to determine if you are potentially affected. Better than that, we'd like to ascertain if you are definitely affected. That would be cool. Depending on the kind of library you're using, the kind of dependency you have, this could be complex. So what kind of different packages can a vulnerability manifest in? Well, there are 2 things of lingo that we use at Semgrep, okay? This is kind of specific to our workflows. So it's not as important, but basically some vulnerabilities are what's called reachable, or we can write a reachable rule. Let's suppose that we have a package named foo, and it has a .save method, and that .save method has like a path traversal vuln. Okay, you could potentially control the path you pass to it, and then it'll like overwrite something on your system, or like get access to something on your system. In that case, we might be interested in just if you literally just call, library.save or foo.save or whatever. Literally, we might be able to write a rule that just says, okay, if you call this particular method, like your hose, you're screwed. You have a vulnerability on your hands. This is useful because sometimes quite often, only a subset of your API is vulnerable, right? If I have a package foo that has methods A and B, A might have a vulnerability, like a path traversal vuln or SSRF or whatever, and B might be totally kosher. So in which case, we would only want to give you vulns, we'd only want to issue you findings, like alert you if you are using whichever one I said was vulnerable, A, probably. So that is why we want to write a rule that's specific. We also have upgrade-only rules. So some kinds of packages are less like you import a particular part of it. Some things are like frameworks. Like if Django itself is like kind of like compromised and you use Django for like your web, your HTTP endpoints or whatever, like you're probably kind of hosed. And then the best thing we can do is tell you like, no, it's not that you have like this specific method or this specific thing you imported. Like you just got to upgrade. There's no remediation beyond just upgrading your package. Same can be true for if you use like a command line tool. Let's suppose FFmpeg, right? The thing that does like visual like kind of editing stuff, or audio, whichever. If that thing's compromised, probably you need to install a new version of FFmpeg. So that's what we call upgrade only. We also have rules that do that. So we want a better way to write these rules that I just identified here, right? We want a way that will be mostly autonomous, so free of human intervention, like because before I told you Max had to do it all by hand. Discriminating, it should be able to understand when you can write a reachable versus upgrade only rule. It should be auditable. We should be able to determine if it's correct at any given point. This is where the general ideas of this talk come into play, by the way, when we talk about correctness and auditability and reliability. And it should also be precise in that we should be able to know what parts of the library's API are vulnerable in this CVE. This is our problem statement. We will now talk about how we solve this problem statement, and the engineering techniques we use to do that are going to belie the overall goals and motives behind this talk, or takeaways, I suppose, is another way to say. Does anyone have any questions at this point in time? My middle name is Jeffrey, in case you were wondering. Great. Okay, cool. No questions means we keep going. All right. So we have a problem statement. Let's automatically write Semgrep rules from CVEs. In the year of our Lord 2026, the answer is obvious. Let's ask our good friend, Mr. Claude, to do it. However, this is a problem that has existed for kind of a while. And the tool I will talk about, which is our approach to doing this, was developed in 2024 before we had agentic coding assistants. So there are 3 lessons I think are actually useful for 2026 in light of this approach that we had in 2024. One is that non-agentic code is deliberate code. When you tell an agent to do a thing, you're telling it what you want. You're telling it the end state. That's what we call something that's very shoot. The word is missing from me, but it is you just specify what you want, and then the actual way that the how of it is unspecified. That is not deliberate. You're leaving that whole thing abstract. You have no idea how it'll get done. Very undeliberate. Agentic coding workflows are unpredictable. I'm sure that all of us here are familiar with asking an agent to do a thing, and it's like, no, or rather it's like yes, but it says the wrong thing, or it says yes and it does the wrong thing, or it says yes and then it says I did it perfectly, and then it only did part of the ways, right? We're all very familiar with this kind of thing. It's unpredictable. We have no idea if it's going to do it right, so you can get inconsistent results, which is not what you want to say when the CISO comes up to you and is like, why did we not catch that bug in the Linux kernel? Well, sorry, boss, it's because our agent was unpredictable. Like, sure, but like also, I don't know, our job is to make sure that we don't have those things happen. So let's make sure that doesn't happen. 3 is I'd say that structured code is easier to test, easier to reason about, and is easier to improve upon. So when I decompose a problem statement into subroutines or subproblems, right? Each of those subproblems can be tested for its own independent correctness. It can be retried. It can be improved upon in a black box. But overall, the system as a whole is not like this big jumble where the black box is this whole middle part, but each individual part is a modular unit that can be easily structured and improved. So I think that these things are all things that I believe to be true of code. And I think that right now, asking Claude Code to do it loses us these things. So let's talk about how we can preserve these things while keeping the cool stuff about Claude Code. So we're going to take this workflow that could be agentic, but we're going to see how Semgrep, or I, brought it down to earth as mostly deterministic code. There is some LLMs in there, but it's mostly deterministic, and I think that gives us a great boon. The other important thing I should tell you is that this was invented in 2024. And 2024, if you weren't keeping track, was a great year for music. We had Chappell Roan, we had Sabrina Carpenter, we had Charlie XCX, we had the Eras Tour. So basically, this internal tool, I called Brat. It's called Brat. I found great fun in doing that. So I'm going to be when I refer to Brat, it is the name of this tool. Great, thank you. All right. I'm just going to skip this part. Or actually, I'm going to tell you that Brat is 3 parts. I'm going to elucidate these parts, which are the research part, the test gen part, and the rule generation part. And we'll talk about what that means right now. So first thing, when we are given as an input a CVE, a vulnerability in a package, some package like foo or LangChain or whatever, we want to research it. We want to determine information about it because that's what a human would do, right? It would read, what does this package do? How do people use it, etc. So we'll scrape the README of the library using an LLM. We'll scrape the online API documentation to understand what stuff in the library is fit for open consumption, for external consumption. We'll search GitHub for how do people actually use this package. And most importantly, we'll build a code graph or a call graph. So that's a graph where the nodes are functions and the edges are given by which functions call which other functions. So if A calls B, there might be an edge from A to B. That is a call graph. And this is going to be very helpful because we're going to use it to transitively determine which functions are affected by the changes that are induced by a vulnerabilities patch commit. And I'll talk a little bit about that more in a second. So 2, we're going to do what's called test generation. When you write a Semgrep rule, write a query, you can use it on a file and it will flag for you in the file the parts where the vulnerability is. Megan was talking about this earlier when she was talking about the playground. The playground is an example of this. On the left, you have the rule. On the right, you have what's called the test file. And you can see where the rule matches, what lines of code that it flags as findings. So importantly, we want to generate a test file that shows us where we expect to match. Do we expect to match foo.bar or foo.baz or whatever? And the important thing is that each function is treated independently. We have an independent subproblem thing where each individual part of a package's API we can treat in parallel. I'm leaving this a little abstract and not explaining too well. I'm going to show you pictures later. So I'll leave this here for now. And then finally, once we have a test file which shows where we expect to match, we can use that as a source of truth, a verifiable, machine checkable source of truth, to see whether or not the rule that we generate, the query, is able to properly match on the lines that we want it to match on, right? So this is kind of the same thing as like a verifiable determinant or verifiable non-determinism, right? If you're familiar with like theorem provers or whatever, this is a kind of a similar idea where if you use an AI, it's best if the AI's output can be checked by like a trusted thing that like is deterministic. And if so, then you can use non-determinism to the moon because you've constructed a deterministic cage around it or a net or something. So this is the net, or the test file is the net. So using this test file and the rule, we can determine, oh, did we match 3 out of the 5 places we expected to match? And then we can stitch it all together into a single rule. But the important part is that each of these different functions can be done in parallel and can be done independently in a way that it makes us easy to compose into a larger verified solution. So I'd say that composability is also a large thing I would like to stress about how we solve problems in the real world and how we solve problems in a way that we can scale with non-determinism in the mix. So the important thing is that this whole pipeline we've been talking about is deterministic wherever it can be deterministic and only has a few parts that are non-deterministic, okay? That's a cool thing I'd like to point out here. Any questions at this point in time?
Hi, I'm Raji, and I have a question.
Hi,
As
yeah.
a beginner, when I want to, can I use the Semgrep for practicing purpose? And how do I use it?
Yeah, so you can just go to the playground, playground.semrep.dev, I think, or semrep.playground.dev, I don't know. Semrep.dev/playground. And then that'll let you like try out writing Semrep rules against real code. I think that Megan linked it earlier. Also, we have I believe we still have we still have semrep.dev/learn. Or no, actually, let's not do that one. We have what's called Semrep Academy, which is like where you can take some courses for free that teach you how to like write SEMREP rules, or in general just kind of like teach some security stuff that you should know. So I would say that all of those are excellent resources for learning things having to do with SEMREP.
Oh, okay. Could you please keep in the chat so I can make a note?
Yeah, let me do that.
Thank you.
Oops, sorry, not there. Boom. Okay, Amanda already did it. She beat me to it. She's so good. Damn. All right, well, I'm obscure. Or obsolete, not obscure. Okay, cool. Thank you for asking that. Anyone else have a question at this time? Or else hold your peace. And by hold your peace, I mean, I'm just going to move on. Cool. Okay, works for me. We're still live. We're still rolling. Yeah, we're still rolling. Okay. Okay. The other thing to note about vulnerabilities is they can be standalone or a library. I don't care so much about this. Let's skip this. It is in my live talk too. I don't care. Okay, cool. Let's talk about this code graph idea. So the insight I would like to say is that vulnerable code is vulnerable typically because it calls vulnerable code. That was a lot of me saying vulnerable and code a lot. Let me break that down. So let's suppose that there's a particular point in your library where you call a database and then you have like an input that goes there. Usually the vulnerability happens because other parts of your code call that initial vulnerable part of your code, right? So transitively, we have this thing where if you're vulnerable and I call you, I am now vulnerable. So we can exploit this property in practice, right? So remember Max's CVE, I said there was like one deeply nested utility function that was private, and that was changed by the patching commit. That heavily implies to me that the vulnerability had to do with the behavior of that function that we changed, right? Because otherwise, how would I fix the vulnerability by fixing that particular function if it wasn't a problem with the function? It's if it looks like a duck and talks like a duck, it's a duck, right? So similar kind of idea here. So the next thing that's important is that any caller of that private utility function is potentially compromised. So if we traverse the call graph backwards, we might be able to find outwardly, externally facing functions that users can consume, and that will tell us how you might vulnerably consume this package. So I have this nicely visualized for you in this diagram where if I have a database call here and I have this helper that calls the database call and the patch commit edited this helper, probably this helper is the problem. So this function that calls the helper is now potentially vulnerable. And because this guy is potentially vulnerable, this exposed API function that calls this guy is now also potentially vulnerable. So it's potentially vulnerable all the way down. It's elephants all the way down. But we can traverse it backwards all the way until we find an exposed external function that we can then write a rule for. Okay, that's the basic idea. So how do we build such a code graph? Well, thankfully, Semgrep is what I called a program analysis tool. So we can use the Semgrep engine, which kind of already understands, okay, what functions exist in the code, what functions call other functions. Semgrep already does this. This is literally Semgrep's job. So we can piggyback off that to build a tool that uses that and it kind of just like builds a code graph from Semgrep's instituted knowledge about the code base. So we're going to do that. We're going to build this directed graph again, where functions are nodes and caller-callee relationships are edges. We're going to fill that up, and then we're going to mark functions changed by the patch commit as vulnerable. So that's this purple guy right here, right? Mark that as vulnerable. Then transitively, we're going to go back. Basically, this is just doing like a BFS, right? A breadth first search. We do a search backwards through the graph, and then anything that calls the purple guy is now purple. And anything that calls those purple guys is now purple. And we keep going until there's no more purple. Well, there's no more like things to mark as purple, right? I wish I had a little diagram for you, but I don't. So you're gonna have to imagine the purple in your own head. Sorry. This is cool because this makes code graph generation deterministic. If I give you the same code and the same patch commit change, so the same functions are changed, we know the same API functions transitively will be changed by that. So this is all deterministic. We haven't even brought any non-determinism into it so far. This is very cool because it's, if I may say so myself, because it's verifiable, it's trustable, and there's no like, oh, like you told me like this thing like potentially calls the vulnerable guy, but are you sure? No, we know for sure this is true. I mean, up to like bugs or whatever, but like at least this leaves us certainty without room for like the 5% human error or whatever. Whereas like I would say that there's a lot more uncertainty if you can't even trust the non-term determinism, or it changes on different runs. So code graph generation itself is deterministic, but it's built upon fundamental program analysis methods and not LLMs. And we only use AI for particular well-scoped subroutines like scraping API docs, parsing READMEs, etc. So we've kind of scoped our usage of AI to very particular things. So it's a very anti-AI take from me, where I feel like some AI take is kind of like, use it for everything. I'm telling you, don't use it for everything. Use it for what makes sense. That is a big lesson I'd like to take away from this. Let me show you an example of this. So this is actually something that Semgrep or Brat, this tool I'm talking about, right, generates. So in this particular package, I actually don't remember what the package is, but I pulled this from one of our real examples. The starting node is the initial patch commit edited node. So this remove DTD markup declarations function was changed by the patch commit. That means that we think that's vulnerable. This function clean also called, so actually I lied to you. The edge is called by. If function A is called by function B, there's an edge from A to B. Sorry, I'm a dirty liar. You can tar and feather me later virtually if you feel strongly about that. Historical reference for you. So clean calls remove DTD markup declarations. That means that we believe that clean is also vulnerable. But is SVG calls clean, so we believe that is SVG is vulnerable. Additionally, I'm not going to tell you how we know this yet, but we do know that is SVG is what's called an external node. When people import this package, they actually do import and call is SVG, but they don't import and call clean or remove DTD markup declarations. That means that when we write a Semgrep rule, we want to write it only for is SVG and not clean and remove DTD markup declarations. Does that make sense? I mean, we could write a rule that marked for these things, but we'd rather not. It'd be kind of wasteful. It would take time. It would take security researcher time. It's annoying. So let's scope our rules, our queries, only to things that we know for certain that consumers will care about calling or will actually can call. Okay. If this makes sense, I'm doing kind of a suffice to show thing where I'm going to work backwards and show you how we derive this external node thing. Cool. Okay. Geez. So we're going to move forward from that or backwards, whichever. All right. By the way, the other one thing I want to tell you is these things get complicated. This is not even the most complicated example I have, but a really complicated example you would not be able to understand while being on the slide. But like these things get big where it's like this thing might be the starting node, and it's called by this, which is called by these, which is called by this, it's called by this, it's called by this, called by this, and then boom, 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 boom. Like this is not even the most complex things I've seen. This has what, like, I don't know, 25 nodes. I have seen code graphs that have like 5,000, just working back from the patch commit. Usually Java is actually really bad. Java is a bunch of methods. It's crazy. So the other strong suit of this deterministic approach is like, as a human, as an AI, even if we want to do this as an agent, it'd have to go and look at this, and then look at this, and then look at this, and then look at this. And it could do that. But like, what's the percentage chance that the AI gets confused and messes something up? 5%? You want to multiply that every single time that you do this, right? Because that's how the probabilities work, is that you're at every single point you have a probability of messing up, and they compound. Who learned about compound interest in school? It's like not quite the same thing, but like similar. The probabilities multiply. So you don't want to risk this where like at any given point in this very long, arduous process, your AI might go rogue, and it won't go Skynet on you, but it'll mess up, So that's not good. So the advantage of having this be deterministic is I always know that this is the output for the same input parameters. It's what's called pure in a functional programming context. Okay. So very, very important when your problem statements are very complex. All right. Okay, so let's talk about how we filter to public nodes so I can finish off this suffice to show. The transitive closure of a project, which is a fancy word that mathematicians made up to make computer science or programmers feel bad about themselves for not knowing enough math. It just means the functions that call each other. All right, but if you want to sound really fancy at a party, say transitive closure. There might be a bunch of functions, a lot of functions. We don't want to deal with that. We cannot possibly write a rule for all of them. So Brat has a filtering pass to identify only the public nodes. Here's how we do it. We're going to make like hundreds of calls to GitHub's API. Before I go more into this, I want everyone here, if you work at GitHub, to raise your hand and then tell me you're not going to snitch on me for this. Because if you work at GitHub, I'm lying. We don't do this. We do not make hundreds and thousands of API requests to GitHub. It doesn't happen. And now, have I gotten rate limited by GitHub? Hundreds of times. Many, many times. Very bad. Don't tell GitHub. But we do this, yes. We make a lot of queries to GitHub to determine what functions are actually used by, say, TensorFlow or LangChain or whatever. We make a lot of such queries. And then if we suspect a symbol like bar of being used, so okay, sorry, let me clarify. If we have like TensorFlow dot, I don't know, save, and we think that method could be vulnerable, we're gonna go search GitHub for the strings TensorFlow and save, and we're gonna like use Semgrep's program analysis to pare that down more faithfully to determine if people actually can import that symbol. Because the problem with languages like Python is we don't know. We don't know if a given function can be imported, and we want to use the real open source code to kind of tell us whether or not that's the case. And then we use Semgrep queries to actually determine, because like searching for TensorFlow and save could give you false positives, right? Of course. I actually have a diagram for you. I actually bothered to make a diagram. You're welcome. Sorry, yeah. Wait. Did someone say that, or was that an echo of me? Might have been an echo of me. Huh, interesting. Okay. Yeah, no. Okay. So let's suppose that we think that a package called foo has a method called bar, and that thing might be used. We're wondering, do people use this in real life? So we're going to search GitHub for literally these two strings, import foo and bar. That'll give us two such examples. We might have this one, which is a valid use of foo.bar, right? That's real. Or this one, which is not. But do you agree with me that if I search GitHub for like the or of both these things, or the and, I guess, we would turn up with both. So this is what we call a false positive, which is also called bad, unfortunate. Do not pass go, do not collect $200. So this is not good. So what we do is we use Semgrep, and we can craft a Semgrep rule, or just generally kind of use Semgrep to determine if this is a false positive. So I'm not going to go too deep into how we do that because it's not actually that important to the talk, but rest assured that there are ways to use code indexers and compilers or LSPs or whatever to actually determine if this is the case. And this just happens to be how we do it. And if you're with me on that, then boom, this is how we figure out what the public nodes in our project are. Oops, what? Okay, are people with me for this? Because as they say, if you're not with me, you're against me. And if you're against me, then what are you doing in my talk? No, I'm joking. Okay, so the next thing I wanted to talk about is this test gen and rule gen idea. Naive approach. Let's suppose I got food.bar, food.baz, food.cooks or whatever, and I think that all of them are afflicted. And I give them to the agent, I tell it, generate to me the rule, and I call it a day. Now, this can go wrong for numerous reasons. One, early attempts, very often the agent would just generate an invalid Semgrep rule. It wasn't even an agent back then. We didn't have agents in 2024. We would ask the LLM and it would generate to us an invalid Semgrep rule. Very, very annoying. This doesn't happen as much now. Like agents can generate valid Semgrep rules. I trust in that in today's world. But other problems, I don't know if you guys have ever done this, but like you give an agent 20 things. You say, do this 20 times, and it gives you like 19 results. I don't know about you, but this is the story of my life. This happens all the time. Like agents will just drop stuff and they'll forget about stuff, or they'll dupe stuff. There's not an instituted way of checking statically that it actually does this. Your best bet is like to retry, which you can do, but it's annoying. So giving all of the afflicted functions to the agent and trying it is actually really bad. It might not work. Or you might get a rule that doesn't even match what you wanted to match. You just asked the agent for a rule. It was like, hey, boss, here's a rule. It was a valid rule, but it didn't generate to it properly. So the key insight here, which is kind of specific to this problem statement, but I would encourage you to find similar things in your own problem statements in your day-to-day jobs, is independent functions in the package are independent. My ability to match foo.bar is independent of my ability to match foo.baz. It doesn't really matter. I can test it independently, and I can detect them independently. So we can do test file generation and rule generation on a per function or per symbol, the word we might use is, a per function basis by decomposing our problem into subtasks, okay? It's like merge sort or whatever. It's like we want to take our complex problem and earth it into smaller problems that can be done in parallel, or better than in parallel, just independently verifiable. So the high level of this is if I wanted to write a rule that flags foo.bar and foo.baz, okay? So we know for sure foo.bar and foo.baz are vulnerable. We'd now like to write a rule that matches both. I'm going to ask an LLM independently to generate test code that uses foo.bar and foo.baz. And then I'm going to ask it to leave what's called test annotations, which are places that tell Semgrep, hey, I'm expecting a match here. Hey, I'm not expecting a match here. This is how we'll know where the thing should match. But we only do it per symbol. So if I have 50 functions in a package, it makes it much easier for the LLM because it has to think about only one thing at once, which I think you also kind of know is like a thing with agents. The more context you give it, the greater chance that it'll drop something, it'll mess something up. Same thing is true of you and I, So we ask an LLM to generate a pattern that matches foo.bar and a pattern that matches foo.baz. Then we test each pattern independently. These are verifiable and verifiable independently. And if either of them fail, we can rerun just that function. And then we can stitch all the test files together and stitch all the patterns together. Oh my God, Brandon, this is so hard to follow and understand. Well, thank you, dear reader, because I have a diagram. You're welcome. Okay, cool. Let's suppose we have foo.bar and foo.baz. We're going to put them into an LLM and obtain what's called a test file for both. So this test file says rule ID. It means we're expecting a match on this line that uses foo.baz. And this test file says rule ID. Oh, shoot, this new line shouldn't be here. Sorry. Assume that's not here. This rule ID, which says that there should be a match on the next line, which uses foo.bar. So for instance, foo.baz might be a function where it has like a vulnerable, a keyword parameter called vulnerable. And if you pass vulnerable equals true into it, it will be vulnerable. Now, why anyone would ever call a function that has vulnerable equals true as a parameter is beyond me. But let's suppose that this exists, because this kind of does in some contexts. We need to write a pattern that matches only uses of foo.baz where vulnerable equals true is passed in. Whereas foo.bar might be a function where like anytime you call it is vulnerable. So the pattern for both might look like this. If you're not familiar with some query context or syntax, it doesn't matter. It's not super important. But the point is that this is what you would write. So we write foo.baz where we don't care about what the other parameters are. We just care that some parameter to it is vulnerable equals true. And for foo.bar, it looks like I've mixed these up. Sorry, tar and feather me later. My bad. But this function might itself just be vulnerable. So we might write both of these patterns and say that that's what we want. And the cool thing that we can do, she got some water. Whoops. The cool thing that we can do is that we can then take these patterns and stitch them up into one. Whoa. Sorry. If you make like a this motion with the trackpad on my laptop, it rotates the slides. I just learned that now. I just thought it was interesting. Whoa. Anyways, if you take these patterns and you stitch them together into one rule, you get something like this. It's not really important. It's just important that you can do that, right? So if we independently come up with these patterns, now we have a rule that matches either. Or sorry, we have a rule that matches both. Similarly, this is going to be a little gross to any of you that have the same principles as me, but turns out if you take a Python program and another Python program and you just literally cat them together, you get a valid Python program. So turns out you can just take both these test files and stitch them together into one file, and now it's a test file for both. So God bless composability of programming language statements, I guess. EBNF grammars, whatever. Okay, this is the whole process. So we independently generate the test files. We independently generate the patterns from them. We verify whether or not the pattern matches these test files, and we retry if that's not the case. And then once we're happy with it, we stitch them together into a full test file and a full Semgrep rule. Any questions on this whole process? Great. Here. The cool thing about composability is we cannot accidentally drop a symbol. I just told you this thing about how if I give an agent 20 things, it might give me back 19. If we handle each thing independently, we can't do that. We will know for sure if we drop something. And we can always retry. So that's pretty cool. We can audit the component of each rule that's responsible for the component of the test file. So each function, we can determine whether or not it matches. And I would posit to you, the system is more composable and understandable. If I want to incrementally improve test file generation or rule generation, I can do that because I actually know what the algorithm to do it is. I can edit, the file that's responsible for rule gen. I can slap more retries on it. I can, edit the prompt that does the generation. But if I just edit the prompt for the whole problem statement, like the general prompt I give to an agent, that's going to be much harder. The agent might just mess up. So failures are isolated and retryable without having us have to retry the whole thing. That's really what grinds my gears sometimes, is like to retry an agent, I'll have to retry the whole thing. Takes ages. Do not like that. So this is the whole algorithm. Over 2 years of existence, Brat has co-authored or authored nearly 3,500 rules, which is a lot of rules. We collect metrics on the helpfulness. So about 20% of them are what we call ready to merge, which is that they, with very little or like almost no human review, we know they're correct and we can just kind of merge them in. There's still a human in the loop, but like there's only like 2 minutes of work, 5 minutes of work necessary. Some of them are very helpful, so that's like another 20%. Some of them are just helpful, that's like a 40%. Some of them are not helpful, harder cases, that's like 16%, 17%. And then these categories are ones we don't really collect data for that much. That's like 5% other ones that are not super important. So overall, mostly helpful, which ideally you'd like to hear from us investing time into this tool and from me talking about it for like 45 minutes. If I were to give you like nonsense numbers that are approximately correct, we could give you a conservative estimate that like a ready to merge rule takes like 10 minutes of researcher time. A very helpful rule might take like 20 minutes of researcher time. A helpful rule might take 45 minutes of researcher time. Whereas before, a researcher might spend like an hour writing a rule. That's by our previous estimates. So proportionally, Brat has saved 40%, probably a bit more because these were conservative estimates over its years of existence, which is pretty cool. It's a pretty good decrease in expensive human resources. And also, I would say it's pretty cool because Brat has given us the ability to do new things that we can't do. Let's suppose that we have a night where 200 CVEs are filed. The cool thing is that Brat is not a human. It is a machine that is runnable in parallel. So we can run all of those 200 rules at the same time. It's not just researcher time, it's researcher time in parallel. So if there's a night where like 200 rules or CVEs are filed, by the time you wake up in the morning, there could be 200 rules that are written. It's not guaranteed that all of those 200 rules are correct, but at the very least, we've done some proportion of the work up front. So that's cool. We can also backfill rules en masse. So there's a lot of CVEs out there, and we only have time to deal with like the high in severity ones. And we also don't have time to deal with all of them. So Brat has made it so that we can backfill those high in severity rules all the way back to 2017 that the researchers didn't have time to write. They only did like back to like 2020 or 2019. So that's cool. Also, we can add new languages really easily. If we want to add rules for Rust and we don't previously support Rust, we can do that all in one night. So the cool thing about these deterministic, well, I guess just like programmatic workflows is that they do not require humans they're parallelizable is the nice thing about them. I did a case study where I asked an agent to try to solve a given CVE because I wanted to compare our deterministic workflow versus an agent. And to be sure, there were some CVEs where the agent was able to get in a good way, in a way that was similar to a brat. But the problem was the agent said this. It's not really important, but like this is from the dialogue. The agent said the vulnerability is in this function called dvalue.parse. Because the unflattened function doesn't block proto keys. These are just words. But the point I'm trying to say is the agent itself recognized that the problem is in this unflattened function. What the agent didn't know is that the unflattened function is exposed by the library. It's usable. So the agent generated this rule. This rule only looks for dvalue.parse. Here it looks for .parse from dvalue. All of this looks for dvalue.parse, but it doesn't look for dvalue.unflatten, which is a valid exposed entry point. And how do I know this? I know this because when I ran the code graph through Brat identified that in this CVE, hydrate is a function that was changed by the patch commit. That function is called by unflatten, and unflatten is called by parse. It's true, but it also knew that there were, by looking through GitHub, making thousands of API requests to GitHub, sorry GitHub, that these two functions are exposed and the real functions that are called. So the point I'm trying to get across to you is like, yes, you can go and ask the agent, solve the CVE for me, and it might give you devalue.parse, and you might be happy about that. But you have no way of knowing if its answer was complete, if it was actually fully true. So the nice thing about having this like code graph that's deterministic, that is complete, is that you know for sure that you've dotted your I's and crossed your T's. You've gone and looked at every single thing that you wanted to look at. And I think that's really cool. So that is generally what I'd say the strength of a deterministic workflow is, of an auditable, trustable, verifiable subproblem. Okay, so to summarize what we kind of learned today in this case study of this particular problem that Semgrep has to solve, but is maybe applicable to other things. Agents are good. They are. Don't get me wrong. They're good for simple cases. Sometimes they'll skip steps or have leaps in logic. But on the whole, I'd say they're not really auditable or composable, right? They will come up with whatever problem statement that they have, and it's unclear sometimes what the approach that they took is. Or if you do know what approach they took, it's unclear how you could improve upon it, right? It'll be new each time. And sometimes it'll miss non-obvious paths. Whereas Brat or deterministic workflows in general that are mostly deterministic, right, have a lot of steps that are independently verifiable. They have composable, retriable results. They're subtask oriented, and they're improvable at each of those juncture points. And importantly, the code is not, what I'll say, ephemeral. You ever had an agent like write a script that it only uses once and then like it gets rid of it? Like that's the weakness of like, what I'll say is I don't know, garbage software, or that's not quite what I mean. Like, software that you just kind of spin up and throw away. That's the weakness of that, is like you can't improve on it later on the next time you want something similar. So persistent software is nice because you know what it does and you can make improvements there. Although it is nice when an agent can, come up with a script in like five seconds. Like, don't get me wrong, I love it when it can do that. But for like persistent software we want to do well in general, this is nice. So here's my conclusion. Shareholders and AI enthusiasts, I live in San Francisco, I'm familiar with both, okay? They might purport to you that problems are best solved by asking an agent. Throw more money into Anthropic or OpenAI or whatever. I'm not paid by either of them, okay? Trust me. Although I wish, Jesus Christ. In many cases, they're correct. Like, go ahead and dispatch the agent. Do your thing. If you want to, I don't know, hook up your freaking barbecue to a Kubernetes cluster, which I think our head of engineering literally did. Sure, go like make that your weekend vibe project. Fine. But there are problems that do have important decomposable discrete parts, and they're better left in GOFC, good old-fashioned code land, I purport to you. So deterministic workflows plus non-deterministic LLMs. I'm not trying to tell you don't use LLMs. I'm not trying to tell you don't use agents. But let's be careful. When there is a problem that could not be solved by an agent, maybe let's make some code that solves it instead. Maybe make the agent make the code. Sure. But then let's improve on the code. Let's make it persistent. Let's make it something that we understand, as opposed to shelling out to the agent the whole time. I think that, and Semgrep thinks that deterministic workflows plus non-deterministic LLMs